Okay, hello logic class. I want to talk about numbers, and specifically I want to talk about the relationship between real numbers, rational numbers, integers, and natural numbers. But first, I want to talk about complex numbers, because it's actually the best way to understand what's going on. So okay, let's do it. What the hell are complex numbers? Well, okay, I don't want to talk about this actually too much. This is kind of the inspirational example. And alright, we didn't talk about complex numbers much in this class actually, but they did come up in the book a lot. And the idea is, you know, keeping this kind of brief, they're very mysterious. Here's an example of a complex number, 3 plus the square root of negative 25. Ooh, very, very mysterious. You might even say, you know, that you can't take the square root of a negative number or something like that. That is what people said in the 16th century when they first stumbled upon these things, and they wrote it like this for a very long time, and they hated it. And everyone else hated it too and didn't take it seriously. Well, so if this is, you know, I'll just write, you know, very mysterious. I'll just say, well, perhaps if I write it as 3 plus 5 times the square root of negative 1, maybe that's a little bit less mysterious. I think it's still pretty weird. I think this is still very weird. Well, now, instead of talking about the square root of negative numbers, which seems impossible, at least geometrically, now I only ever have to talk about the square root of negative 1 because, you know, everything else can be kind of factored out or something like that. So people hate that. And okay, eventually people start, you know, for I think psychological reasons or something like that, start using a different symbol, I. And now we're at the point where this is maybe like, you know, okay. And actually it's really not okay. You've just kind of hidden the problem away, and you've stopped freaking people out because you've stopped talking about the square root of negative 1. Instead, you've just defined some symbol I that you don't understand and that you have no explanation for to be the square root of negative 1. And so every time you stumble upon the square root of a negative number, you just quickly slip in an I in there before anyone notices, and now you just pretend like everything's okay. This is, of course, what we teach to all of the students in America, like in, you know, Algebra 2 or whatever. Okay, so let's go one more level of abstraction, and let's just think of this as an ordered pair. Okay, I'm not really qualified to be talking about this, and I haven't researched this part of the lecture too much, but somewhere in the 19th century, I believe this is finally the guy, William Rowan Hamilton, which we skipped talking about this year because we skipped talking about quaternions. He was the one who finally took this kind of conceptual leap into fully, so he would say, demystifying the complex numbers by just thinking of them as ordered pairs. And in fact, that's not so mysterious because that's really just what the complex plane does, after all. What is 3 plus 5i? Well, you go, you know, over 3 on the real axis, and you go up 5 in the imaginary axis, and you get to this number, you know, 3 plus 5i. Well, great. Thus, you might very well just consider it to be an ordered pair, 3 comma 5. And okay, so the sort of final project in dealing with complex numbers, in sort of making them seem less weird, is to just completely abstract away from them and sort of pretend that there's no problem, because, like, you know, reality isn't important or anything. Let me just sort of write down all the rules there are about these complex numbers, and then I'll sort of be okay. Okay, and so what people do is they hereby, this is one thing one can do, although I'm not saying you should or shouldn't do this, but you can, basically you can construct the complex numbers out of the real numbers. In other words, anytime you have some reason to write a plus bi, yeah, you have maybe a problem, some might say. Because what the hell is I? Well, it's the square root of negative 1. What does that even mean? Okay, well, I'm going to tell you what it means. Define a plus bi to simply be an ordered pair of real numbers. So, and this is, you know, this is very close to what we do in Algebra 2. we say that every complex number is in the form a plus bi, where a and b are real. And so we might as well almost just be telling you a complex number is just an ordered pair of real numbers. But we don't take this sort of final step into really throwing the I away entirely, and that's what I want to do now. So instead of, so now let me, if a complex number is really just an ordered pair of real numbers, well then I need to tell you how to add these ordered pairs. So I hereby do that. Suppose you have one of these complex number things, and you want to add two of them together. Well, I just stipulate that this is how you add them. You add them by adding the left member of, the sum of two ordered pairs of real numbers is a new ordered pair of real numbers, in which the left member of the ordered pair is the sum of the left members of the other ordered pairs, and this is now this is now b plus d. And of course this conforms to how we are supposed to add complex numbers for whatever reason it is that is usually proven. Usually it's just not proven. In other words, we sort of treat the complex number like a vector, and sort of the sum of two complex numbers is kind of the vector sum. Okay, but you don't have to like this, because I'm just or you don't have to understand this, or you don't have to have any kind of meaning. There doesn't need to be any meaning here. I'm just giving you just a raw definition of how the manipulations of these objects are supposed to work. Okay, well, now let's define complex number multiplication. And so here I deviate from what is normally done. What is normally done to convince an Algebra 2 student that whenever you multiply two complex numbers you get another complex number is to actually sort of deal at the level of like reality or something like that, and multiply out the two complex numbers. Maybe I should do this in a different color. I won't do it in a different color, but I'll put a box around it when I'm done. When I multiply out these two complex numbers, of course, what do I get? I get AC plus ADI plus BCI plus BDI squared. So, okay, BDI squared, but I squared is -1. So here I invoke the like meaning of I or something like that to argue that this should be, you know, whatever it is. Okay, but that's doing math based on reality. I'm not doing math based on reality. I'm doing math based on stipulation. And so here I shall hereby define the product of two complex numbers to be simply AC minus BD, comma, AD plus BC. And I think you see that this definition does what we want it to do. Okay, I think there's like even like sort of smarter things that we can sort of say here about the philosophy of mathematics, but I kind of won't now. Let's just push on. Hey, I noticed something. What I notice is that when I add AB plus 0, 0, then what happens? Well, if I just follow my rule of addition, then I just get A plus B. So that makes me happy because it means that I have found a additive identity element. It's the ordered pair 0, 0. And okay. I got another thing that I noticed, which is that if you multiply A plus B times 1, 0, don't ask me how I came up with that, but it's pretty clear how I did it, that now using my sort of blind definition of complex number multiplication, what do I get? Well, I get, hope I'm not in the way here, what I get is AC, so A times 1 minus BD, so that's minus B times 0, comma, AD, so A times 0, plus BC, so that's B times 1. Okay, and now all of these, minuses and pluses and times and stuff inside here are all just operations on real numbers. So, whereas that's actually a philosophical thing that I will draw some attention to, that the dot symbol appearing sort of multiple times is actually two very different dots. This dot is the multiplication of complex numbers, or the multiplications of ordered pairs of real numbers, which has been previously defined. But this dot the dot of just basic real number multiplication, because you know, the elements of the ordered pairs are all real numbers. Anyway, what do you get here? Of course, you get A, comma B, and therefore, what we've just demonstrated is that every ordered pair A, comma B has, or I guess what I've just discovered is that 1, comma 0 is the multiplicative identity. That's what I just discovered. Okay. What next? This is taking too long. Also, you may, as a sort of exercise, an algebra 2 exercise or something like that, you can sort of find the multiplicative inverse of any number, of any complex number. What is 1 over A plus BI? Well, let's just do it sort of off script, so to speak. This is like my scratch work in the margins. This is going to be 1 over A plus BI, and then it's the thing you learn in, like, you know, pre-calc or something to multiply by the conjugate, and when you multiply by A minus BI, what do you get? You get A minus BI over A squared plus B squared, because it's like minus BI squared, so A squared plus B squared. And that's kind of nice, because it means that this thing is now in standard form. And so, inspired by that, I'll put a red box around it, because it's not really part of my theory, it's just some scratch work. I can now state, sort of for the record, that if you give me any arbitrary ordered pair A, comma B, and you multiply it by A over A squared plus B squared, comma, negative B over A squared plus B squared. And here I note that this doesn't work if A and B are both 0, but if but every other case it works. So the only time this doesn't work is if A and B are both 0, and in fact that shows you that 0, comma 0, the additive identity element, does not have a multiplicative inverse. But for any other number, when you multiply these out, I promise you that you're going to get 1, 0. And what does that show? It shows that every number has a multiplicative inverse. And I guess the boring one is the additive inverse. I should have done that first. That AB plus just negative A, negative B will always give you back 0, 0, which is the additive inverse. Okay, what if so I'm just going to write like etc. or something like that. I think I've proven my point. The point I've proven is that we may construct the complex numbers out of the real numbers. If I already know what real numbers are, or I'm willing to temporarily suppose that I have the real numbers, that they're well defined, that they're well understood, that there are no problems with them, that they exist, that I have them in my hand, that real number addition, multiplication, etc. Makes total sense, then I may define the complex numbers by breaking them into sort of pieces of real numbers. And it was so easy that I sort of, did it in 5 minutes or something like that. And you're kind of encouraged in pre-calculus nowadays to, by the very use of the 3 plus 5i notation, and by the fact that we discourage the 3 plus root negative 25 notation, is an indication that we don't want you to think too hard about these things and what they really mean, but we want you to simply just perform sort of computations with them and don't kind of worry about it too much. And in some sense you don't need to worry about it because it all quote unquote works out, right? And what were we sort of screwing around with here? What we were screwing around with was the proof that if you adopt these two definitions, then of addition and multiplication, then you can follow all these rules, and the rules all tell you that the complex numbers form a field. And there's the closed under addition, the closed under multiplication, as we've seen here. There's an additive identity, there's a multiplicative identity, there are additive inverses, there are multiplicative inverses, distributive property, okay, skip all that, whatever. And hey, since the complex numbers do all the same things that the real numbers do, hey, aren't the real numbers a field, etc., etc., then maybe we shouldn't worry about the complex numbers too much. They're just this new kind of number. And if you worry that they maybe sort of don't exist or something like that, that's a reasonable thing to worry about. Well, don't worry, because if you believe in the real numbers but you don't believe in the complex numbers, then now you should believe in the complex numbers because I just built them out of the real numbers. All right, long-winded intro. Last thing maybe to say is if you are interested in sort of realism, do you feel sort of really that the complex numbers are just ordered pairs of real numbers? Are they just really that, or are they something kind of else? You know, can you fully sort of reduce them down to just pairs of reals, or do they have some other kind of true meaning or something? I'm not going to dwell on that. Okay, now I'm going to try to repeat this entire thing, but I'm skipping the construction of the real numbers from the rationals, because that's really hard. So let's now put all that stuff behind, and now let's try to deal with the rationals. So there's this project of sort of reduction, right? I don't need a world in which I have complex numbers because I can build them out of reals. I can build reals out of rationals. That's harder. Can I build rationals out of something more simple? Yes, I can. So now the plan is, build Q, the set of rational numbers, out of Z, the set of integers. Okay, let's go. Sort of, what is 2/3? This is what I did such a terrible job in class on Tuesday trying to explain. What I should have said was what I'm about to say now, which is, what the hell is 2/3 really? What is this? Suppose you don't know. So, okay, so now what I want you to do is to put you in the frame of mind in which you are as kind of skeptical and weirded out by rationals as you perhaps actually are about complex numbers. If you're so skeptical and weirded out about complex numbers and you don't even know what the hell they even mean and you don't understand them, then we reduce them down to something simpler. So now just imagine that, this fractions, what are fractions? What the hell is a fraction? What is this fraction bar? Ugh, this is disgusting. Get this out of my face. Suppose your hatred and disgust for the fraction bar is equal to your sort of hatred and disgust for the square root of -1, and you find them equally sort of meaningless. Well, can we sort of do something about that? Yeah, I think we can. Let's just define 2/3 to be just an ordered pair of integers. Aha! Represent any fraction as just an ordered pair consisting of the numerator and the denominator. This is brilliant. In other words, I should probably say this somewhere. So okay, yeah, sure. Okay, so now define again or replace. I'm not sure what the correct verb should be, but sort of yeah. So define. Think of this symbol A divided by B as just shorthand for or a nice little notational flourish for the reality. And the reality is that it's just an ordered pair. So that's the symbol for sort of define A divided by B to be just A comma B, where now A and B are integers. So I'm building the rationals out of the integers. And for this, I should assume that I already completely, fully, and totally understand integers. So, okay, great. Good. With that in mind, I hereby give a definition of rational addition. How do I add A comma B plus C comma D? Well, this is already sort of hard enough that maybe I can't do it in my head or something. So let's just kind of go over here for scratch work. Well, scratch work, A over B plus C over D. Okay, yeah, I got this. That's like a thing I learned in 5th grade. That's going to be, AD plus BC over BD. So let's now define the addition of these ordered pairs of integers to be, just AD plus BC comma BD. Great. Putting a red box around this because, once again, this is sort of scratch work, not really part of the theory. Moving right along, What about multiplication? Well, what happens when I multiply two of these ordered pairs of integers, as I shall call them? I kind of know, off script, that when I multiply a plus a over b times c over d, I'm supposed to get ac over bd. So I'll hereby define, looks kind of bad, ac comma bd. I'll hereby define multiplication of these ordered pairs of integers to follow this rule. Okay, and now things are going to get a little bit weird now, maybe not yet. So now let's, the analogy is here on the left. I want to search for the additive identity. Okay, well, already, that's a little bit weird. So maybe I'll trick you a little bit by pushing the problem a little bit farther away, because I want ab plus 0, 1. That seems like a good candidate. 0 over 1. And what is it? A comma b plus 0, 1. Well, if I just mindlessly follow the rules given above for how to add ordered pairs of integers, then I get, what do I get? A, d, so that's a times 1 plus, what am I doing? Plus bc, so plus b times 0, comma, bd, so that's b times 1. And now I will say, once again, as I did before, that there are, in formulas such as this one up here, sort of philosophically kind of different things going on here, right? This plus is rational number addition. This is the plus that I'm defining. I'm defining what it means to add two ordered pairs of integers. But this plus is something else entirely. This is the simple addition of integers. So if a, b, and c, d are integers, then when you multiply two integers, you get an integer. When you add two integers, you get an integer. So once again, I'm assuming that integers are completely well understood, that I have no questions about them, that they exist, and that I know how to multiply them and add them and everything. So I'm defining the addition I'm defining up here the addition of ordered pairs of integers in terms of the already well-known and understood addition of integers. And okay, if you're like a super fancy person now, you're gonna say something like you're gonna start sticking like subscripts on your pluses. If this were like a real class, I would do that. So here, this addition is the addition that's sort of typed to the rationals, whereas this addition is like integer addition. So I'm not going to do that. I'm going to let kind of context guide it, but that's what's really going on here. I'm performing a reduction. Anyway, when you do this, what do you get? Well, sure enough, you get a comma b. And that indicates that 0, comma 1 is the additive identity element for rationals. Right. And seemingly, I can just keep on keeping on here. What, I might have to end this video abruptly. What next? What if I do a comma b plus 0 times 0? No, times, sorry, so I want to now, I want to show that I have found the multiplicative identity. And okay, once again, I'm sort of tricking you a little bit, so it's not like I'm missing this, I'm just pushing the conversation off a little bit. Hey, how about 1 over 1? That's 1, isn't it? Yikes. Okay, and, well, what happens if I just follow this rule? Yeah, then I get, using my rule for multiplication right here, okay, this one's just easy, you just go zoom zoom. So I get a times 1, comma b times 1, and this is a comma b. Okay, so you can't argue with me about this. I really did find an additive identity element, and I really did find a multiplicative identity element because it leaves things unchanged. Alright, and now I want to show that every number has an inverse. Okay, so take a comma b. What seems like the additive inverse of a over b? Well, negative a over b, of course. So why don't I just add to this negative a over b, and hopefully I'll get back 0, the additive identity element, which is this one, right? Maybe some colors are required here, right? What I now have found is that green thing and this purple thing are respectively the additive identity element and the multiplicative identity element for this system I'm inventing. Okay, but now something bad is about to happen, because when I add these two, which intuitively should give me, which should give me 0, 1, it should give me 0, then what happens? I get, what do I get? Let's go back up here and follow the rule, A, D, so that's A, B, plus BC, so B times negative A, so okay, so far so good, comma, B, D, so that's B squared. Okay, so what do we get now? What we get is that this is 0, comma, B squared. Alright, now I'm very sad, because it didn't quite work, right? And in some sense it worked, because what is 0b squared? 0b squared is just 0 over b squared, which we know kind of in our hearts is just 0. So I did sort of get 0 when I added these two together. But on a sort of technical level it didn't work, and the reason why it didn't work on a technical level is because of my choice here in green and purple, well, basically my choice to represent the number that deep in my heart I know to be 0 as 0 over 1 was arbitrary. And so, looking back now, and maybe I should just kind of finish off sort of the problem or something like that, right? What happens if I try to show that the rationals are a field? That's what I'm doing, right? I'm trying to sort of show that I've set up addition and multiplication properly such that every rational number has an additive identity, has an additive inverse and has a multiplicative inverse. So here I was proposing, using my intuition, that negative a comma b is the additive inverse of ab, but it didn't quite work. And now, what is the intuitive multiplicative inverse? Because what is a comma b is really supposed to mean a over b, so it's supposed to be b over a, which you multiply by to get 1, the multiplicative identity. Hopefully you're following all this. And yet, when I do this, it doesn't quite work, because now when I multiply following mindlessly my rule for multiplication, I get ab comma ab. And okay, deep down in my heart, my intuition tells me that's just 1, but it's not the same 1 over 1 of my previous work, which demonstrated that 1 comma 1 was the multiplicative identity element. Okay, so what's happening here is that there's not just one additive identity element and multiplicative identity element. This is what I was kind of saying, right? This is why everything is falling apart. Because deep down, I need 0, 1 to equal 0, 2. But they're not. If you try to represent a rational number as just an ordered pair of integers, it doesn't quite work. Because 0 over 1, 0 comma 1 intuitively should be 0. But 0 over 2 should also intuitively be 0. And, like we just know, once again, off script, we know that 10/3 is 10/15. This is what I was saying in class, but it was more or less incoherent to what I was saying in class because I presented it so badly, and I was trying to do it in 1 minute. This is like a true fact about rational numbers, which I'm trying to model in this artificial construction of the rationals out of the integers. But of course, it's just simply not true that the ordered pair 2 comma 3 and the ordered pair 10 comma 15 are the same ordered pair. They're just not the same ordered pair. This is the ordered pair 2 comma 3 and this is the ordered pair 10 comma 15, and there's just different integers there, so they're just simply not equal. As ordered pairs of integers, they're not equal. Yet we want them to be equal as rational numbers. So I can't just represent a rational seemingly as an ordered pair of integers. Like something more is going on here. Okay. Well, do I have kind of space for all this? Maybe the thing to do is sort of erase. Or maybe I'll just kind of keep writing and then erase or something. Let's see. What should I do? I will, yeah, I'll just erase. And okay, I'll just say one more kind of thing, which is, no, I won't say anything. I'll just leave it like that. Okay, good, 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 good. Okay, so I need to fix this mess. How am I going to fix this mess? I need to somehow make it so that I'm trying to decide what to erase. I guess I'll erase this much. Okay, because I'm still constructing them artificially, but now I need to sort of make it so somehow, I'll just write this, somehow we need the ordered pair 2, 3 to actually equal the ordered pair 10, 15. But you know, they don't or something. And all right, why does 2/3 have to equal 10/15? Well, the intuition behind this, of course, the reason why, once again, kind of off the theory, is because 2/3 equals 10/15. Okay, but I am defining away this divided by symbol, so I can't use that as my justification. So what is sort of true? What must be true about the relationship between 2, 3, 10, and 15 as integers, which will capture the fact that these two fractions are equal? Well, this is true if and only if 2 times 15 equals 3 times 10. In other words, this is starting to come into focus. What I want to say about two fractions, a over b and c over d, once again, this is not part of the theory, this is kind of me thinking in the background. This is true precisely when AD equals BC. And so, if all I have access to, if I'm trying to build, understand, and analyze rational arithmetic in terms of integer arithmetic, then I need to find some way for, I need to find some way for, well, here it is, it's sort of right before me right now, right? I need to find some way for the ordered pair A comma B to equal, or something like that, the ordered pair C comma D when AD equals BC. And okay, to be sort of, maybe this is more clear if I do it with an example, and the example that we've been working with, maybe staying back down here. So like 2/3, for example, when should 2/3 be equal to some fraction A over B? Well, 2/3 should equal some fraction A over B precisely when 2B equals 3A. Okay, so I need to somehow set, sort of repetitive, I need to somehow set 2/3 to be equal to any ordered pair if and only if 2B equals 3A. Okay, and the way you do this is you establish some kind of relationship. So let's say, okay, let the ordered pair A comma B be related to in some kind of way. Now I sort of pick an arbitrary symbol. Okay, I use like a different symbol on my paper, but fancy people will use this symbol. So let AB be, what time is it? Oh boy. Be related to, let the ordered pair AB be related to the ordered pair CD if and only if AD equals BC. Okay, so I am establishing a relationship between ordered pairs of rationals. And now I make some observations about this relationship. Well, first of all, every ordered pair is related to itself. That can be just proved because AB equals AB. So that's nice to know. What's another fact? if AB is related to some ordered pair CD, in other words, this relationship holds, then CD is related to AB. Okay, that seems very sort of silly. In fact, these are supposed to be sort of silly and obvious things. What is this? This says that this relation is reflexive. This says that this relation is symmetric. And finally, this is some kind of advanced math here, which this might be your first time ever seeing this, but if you took other classes where this kind of thing has been done, then maybe you know about this already. The third one, which I'm going to kind of squeeze in here, which is that if AB is related to CD and, this kind of squiggle, and CD is related to EF, then AB is related to EF. And this is just a way of saying that this squiggle relation is transitive. Okay, in other words, I have proved that there is this reflexive, symmetric, and transitive relationship between ordered pairs of integers. And now my conclusion, so this is what's called an equivalence relation. Equivalence relation. And okay, what's an equivalence relation? It's any relationship which is symmetric, reflexive, and transitive. Examples of equivalence relations are equals, parallelism. As long as every line is parallel to itself in Euclidean geometry, that's not outrageous thing to say. Then if L is parallel to M, M is parallel to L. And parallelism is transitive. Congruence is an equivalence relation. Any figure is congruent to itself. If a figure is congruent to another one, then that congruence relation holds in the opposite direction, and the congruence relation is transitive. Similarity of triangles, say, is also an equivalence relation. Every triangle is similar to itself. If one triangle is similar to another, then the similarity holds in the other direction, and similarity is transitive. So there's a huge category of mathematical relationships which have these three properties of being reflexive, symmetric, and transitive. And if we have them, then we call it an equivalence relation. And one thing which I'm not going to go into the details of now, but basically, if you already know about this, great, and if you don't, it's fine too. I am going to actually define, and here comes the sort of conclusion of this whole thing, I'm going to define my rational numbers ultimately to be equivalence classes. So every equivalence relation partitions the entire set of ordered pairs into what are called equivalence classes. And equivalence classes are sets of objects within which all the objects are equivalent. And okay, if you get that, then great, but if not, I'll just kind of cut to the end. What we really are going to do, therefore, is we're going to set 2/3 to be an infinite set of ordered pairs. Not just 2, 3, but also 10, 15, and also, whatever, 4, 6, and also, these are integers after all, so like -2, -3, and etc. Every single ordered pair, which if written as a fraction you would call equal to 2/3, put them all together into one giant set, which is necessarily infinite. And I'm going to actually define, so I sort of abandon this. This, it turns out, is too naive, because there isn't this nice, neat one-to-one matchup between numerator, denominator, and ordered pair of integers. I instead define 2/3 to be the infinite set of all of these ordered pairs. And okay, written a little bit more abstractly, I say that 2/3 is the set of all, you might prefer this, it's the set of all ordered pairs such that that ordered pair is equivalent to 2/3. So there's kind of like this sort of iconic or something ordered pair. There's a word for it, not iconic. Blanking right now. It's the there's a word for that. Jeez. Anyway, it doesn't really matter. 2/3 is the set of all ordered pairs which are equivalent to 2/3. Which really, if we unpack that definition, means that 2/3 is the set of all ordered pairs A, comma B, such that 2B equals 3A. And that kind of turns out to be exactly what you want. And this solves the problem because now I use all those old definitions, but the actual objects themselves, what a rational number really is an equivalence class of ordered pairs of integers which are in the same ratio as 2 is to 3. But that fact can be expressed in the lower level language of integer multiplication. So I use the well understood theory of integer multiplication to express the fact that two fractions are equal to each other, and I define 2/3 to be all of the fractions which are in that relation. And then everything kind of works out. And so finally what you end up with is that 2/3 just equals 4/6. And after all, that's a math fact that you need to be true. And why is that true? Because 2/3 is an infinite set of ordered pairs of rationals, but 4/6 is also an infinite set of ordered pairs of rationals. But it's the infinite set of ordered pairs of rationals which are all in the ratio 4/6. And so in fact, those two are equal because they are both the same infinite set of rationals. Okay, what have we done? We have reduced the entire sort of complicated world and messy world of rationals into sort of simpler integer-based objects. And what this means from a kind of a philosophical point of view or something is that you don't really need to believe in rational numbers at all. If you just believe in the integers, then we can construct, so to speak, the rationals out of the integers. And every single rule about rationals is in fact a rule about pairs of integers, in fact infinite sets of pairs of integers. And the final comment I'll make is one more, is a philosophical one. Here it's maybe almost plausible that a complex number sort of really is an ordered pair of reals. But probably you don't think that 2/3 actually deep down is this infinite set of ordered pairs of integers. But I don't know, maybe it is. It certainly has all the properties that 2/3 is supposed to have. And so there's this kind of a very abstract thing sort of going on here in which we start to maybe not know what the hell 2/3 is. And what is 2/3? I don't know, but I found something which acts exactly like 2/3 acts in every single possible way. And this analysis doesn't require you to understand 2/3. So I have sort of reduced the problem of understanding 2/3 down to the problem of understanding integer arithmetic. So that's kind of an achievement or something like that. Alright, unfortunately I have to do family things now, so there's more to this video, but it might just never happen. But that might be okay. Goodbye. Okay, we're back. Let's wrap this up, because we've come this far, we might as well finish it off. Question, what are integers? In the previous part of this video, we reduced all statements about rational numbers to statements about ordered pairs of integers. So what are integers? Alright, this maybe sounds like a ridiculous question, but of course, the problematic part of integers are the negative ones. So everyone agrees that the whole numbers, the natural numbers, 0, 1, 2, 3, etc., are completely obvious and well understood. They're just, you know, the counting numbers. You can talk about them with piles of rocks or whatever. But these negative things, what are these negative things? What is -5 anyway? You know, whoa, disgusting. So, once again, we shall engage in this exercise in which we model integers using, as a background theory, the theory of natural numbers. So, okay, I think we can do this kind of fast because it's exactly analogous to what we just did. Alright, So maybe what are integers? When do you somehow sort of in your life, need to have integers, for example? Well, it's when you're, solving equations, maybe like this: x plus 7 equals 2, and you can think of a number which solves this equation. So you sort of say, oops, there's like no solution or something like that. But if you're stubborn and you want there to be a solution, then you invent something which kind of is supposed to represent this solution. So you maybe invent something called, -5. Well, what is -5? It's the number which, when so you would subtract 7 from both sides. But then the problem is that 2 minus 7 is kind of meaningless, because you can't take 7 from 2, because 7 is more than 2. So you invent this symbol, you invent this number, -5, to mean 2 minus 7. But the problem is, that there are other equations. There are also equations like, maybe I'll go up here, x plus 9 equals 4, and this also doesn't have a solution. How would you like to solve this? You'd like to say 4 minus 9, but 4 minus 9 is meaningless. And so somehow this number that you invent needs to be both 4 minus 9 and also 2 minus 7. And okay, that's really like the heart of the whole thing, right? You want to basically define -5 to be kind of 2 minus 7, but there's no such thing as 2 minus 7, because we are assuming as our background theory only the addition or multiplication of natural numbers, and so there's just no such thing as 2 minus 7. And so what we do is we kind of define -5 to be the ordered pair 2 comma 7, where these numbers are natural numbers. This is kind of what's lurking in the background. Okay, so now the real theory starts. This is now our third time doing this. I'm going to define this thing called, I don't even know how to do this. I guess I'm going to define this thing called A minus B. And, well, actually, sorry. I'm going to define this thing, I'm going to define A minus B. Yeah, that's what I'm doing. I'm defining the sort of symbol A minus B, where perhaps A is smaller than B, but perhaps not. To be just an ordered pair A comma B, where A and B are natural numbers. So, good. Alright, so that's the understanding, that A and B are natural numbers. And now I want to sort of extend subtraction into the case where B might be bigger than A. Okay, so alright, so now doing this, how should I define, oh man, that children screaming downstairs, we will ignore them. How should I define the sum of two of these integer things? Okay, this is kind of maybe a strange question. Now once again, kind of off script. What is AB? It's A minus B, and what happens if we add A minus B to C minus D? Well, we get A plus C minus B plus D. That indicates that I should define A comma B plus C comma D to be A plus C comma B plus D. And like before, I'll put a red box around this because this was just kind of scratch work background thinking. But here you sort of see what's happening, which is because I insist that the elements of the ordered pairs be natural numbers, then I can always add two natural numbers, can't I? So it's really sort of subtraction, which we're explaining in a certain sense, and by explaining I mean explaining it away. Okay, how should I? Interesting. How should I multiply two of these new strange integer things? Well, let's define A comma B times C comma D. And once again, I can't figure, this is sort of weird enough that I can't figure out how to do this in my head. So, you know, I do some scratch work now, and okay, you know, we're pretty comfortable with integers. So how do I multiply A minus B rather, times C minus D? And the answer is, it's like, you know, you just do it, right? It's AC minus AD minus BC plus BD. Ah, okay, great. So then I should define the product of two integers to be the ordered pair of natural numbers, AC plus BD, comma, AD plus BC. Hopefully you appreciate what's going on here without too much comment from me. Because A, B, C, and D are all natural, you know, the product of two natural numbers is a natural number, the sum of two natural numbers is a natural number. So this here, once again, I put it in a red box because it's just the scratch work, is inspiring, you know, this definition. And okay, one more time, we have this conversation, which is that what is really being defined here is addition on the integers. And what's being defined here is multiplication on the integers. So it's these symbols, how to add and how to multiply integers, which are being defined in terms of the lower level and already understood operations of addition and multiplication on naturals. So all of these pluses that you see in these definitions here are not the same kinds of addition. This is the addition on the integers, addition on the naturals is being used to define addition and multiplication on the integers. Okay, whew, good. But I think you're kind of getting it now, so we don't need to dwell on this. Okay, once again, I seek the additive and multiplicative identities. So let's just see that and sort of see if it works. See, you know, maybe that it works. Okay. Well, so you know, sort of note that if I add 0, 0 to AB, what do I get? This we should think of as A minus B, and this is 0 minus 0. Okay, well, what do you get? Well, mindlessly following the rule here, we get, you know, A plus 0, comma, B plus 0, and I think I did that right? Yeah, and that's just A, comma, B. So it seems that everything worked out great, and that this particular ordered pair, 0, comma, 0, is the additive identity for integer addition. Great. But okay, maybe let's just jump to the problem kind of already. What's the problem? The problem is, like before, this number 0, comma 0 is not the only number which has this property, because if I add to an arbitrary ordered pair A, comma B, which we again think of as A minus B, if I add to it like, you know, C, comma C, say, for example, where C is any natural number, well, C minus C is 0. So if I'm adding C minus C intuitively, if I add this, I should also get A, comma B. Do I? Well, just no, right? What do I get? I get A plus C, comma, B plus C. And this is kind of a problem, right? Because once again, kind of off script now or something, how should I interpret A plus C, comma, B plus C? I should interpret it as A minus C, A plus C minus B plus C. Well, that is indeed A minus B, which is supposedly what this kind of means. So now we have sort of like a problem, right? The problem is, this is maybe like a kind of like a different problem. It's not that there is another number which is an additive identity. It's that intuitively A plus B, A comma B plus C comma C should give the same thing as A comma B plus 0 comma 0. And yet it doesn't, because these two ordered pairs are just not the same ordered pairs, right? Here, when I did this, I got A comma B, and I was happy. But here I got just like a different ordered pair. Okay. And maybe that's everything that we need to say. Maybe okay. If we might as well just do this all out. So what's another thing to note? There's also a multiplicative identity. We don't have multiplicative inverses in the naturals, but we do have a multiplicative identity. It's 1. And so what is that number? A comma B. Well, once again, if I choose my symbols sort of carefully, like 1 comma 0, well then everything works out. But because mindlessly following my rule for integer multiplication, what do I get? I get AC, so A times 1 plus B times D, so that's B times 0, comma AD, so that's A times 0 plus BC, so that's B times 1. And when I perform the various operations with natural number addition and multiplication, then I just get A comma B. And so I'm very happy, and I seem to have found my multiplicative identity element. But you know, that's not sort of the only one, right? 2 comma 1 should also be 1. Okay, so I think we kind of see the problem, which I already alluded to, you know, up on top, right? The problem is that 4 minus 9 is also 2 minus 7, and these are all negative 5 in a certain sense. And so what we need, echoing the last problem, what we need somehow is that the ordered pair 4 comma 9 must equal the ordered pair 2 comma 7. Because both of them are just intuitively negative 5. And yet, 4 comma 9 is just not 2 comma 7. If you interpret these as ordered pairs of integers, they are just not the same ordered pair of integers. They are not the same ordered, if you interpret them as ordered pairs of natural numbers, they're not the same ordered pairs of natural numbers. Alright, how do we then solve this problem? Oh man, these kids are so loud. Then what we need we need to somehow characterize what it means for two integers to be equal. So note that A minus B is C minus D if and only if what? So what does it take for an integer of the form A minus B to equal an integer of the form C minus D? Well, this can be rephrased as A plus D is B plus C. Want to like take them to their room or something? Come on, this is really terrible. The video is like ruined. They're like screaming in the room.
You're supposed to make a video now.
Okay, so I think it's pretty clear how I want to proceed. I want to basically make two ordered pairs of naturals equal if they have this relationship to each other. Okay, so let me kind of erase all this stuff to clear a little bit of room, and then we'll do basically exactly what we did last time. We'll establish this equivalence relation. So I hereby define this relation, and two ordered pairs of naturals, A, B, and C, D, should be related to each other if and only if A plus D equals B plus C. And here the pluses, because A, B, C, and D are all natural, A plus D is natural, B plus C is natural, and when you add two naturals you get another natural, and so I've sort of completely characterized now the relationship, I've completely characterized what it means for two integers to be sort of the same in terms of the relationships between the natural numbers that compose them. Okay, and maybe I don't need, let's just erase all this crap, because I think you sort of got the idea there. So okay, and then I can notice some things. What are the things to notice? Well, just like before, A, B is is equivalent to itself. So this is the reflexive property, and then AB is, if AB is equivalent to CD, then CD is equivalent to AB. These can just be checked, sort of tedious checks to see based on this definition of what it means for these two ordered pairs of naturals to be related. This is the symmetric property. And finally, that this relation is transitive. So if AB is related to CD and CD is related to EF, then AB is related to EF. Okay. So, great. This is transitivity. Okay, so that means this is an equivalence relation. If it's an equivalence relation, we shall now, then this equivalence relation partitions this set of ordered pairs of natural numbers up into equivalence classes. And we can define integers to be those equivalence classes. What's an integer? It's an equivalence class of ordered pairs of naturals. So, after all this, here's what we get. And now we're sort of basically kind of done, right? -5, for example. What is -5 really? It's an infinite set of ordered pairs of naturals, each of which are like this, right? 1 minus 6 is -5, but so is 0 minus 5, -5, but so is 2 comma 7, -5, etc. So that's an infinite set, and more specifically, I sort of define, not more specifically, just kind of more matching up to what we did over here. I define -5 as the set of all ordered pairs, A comma B, such that, I guess I'm using sort of, well, okay, I guess the thing to do is to use kind of like, to use 0, 5 as the sort of representative, as the, still blanking on that word. What's the stupid word? As the prototypical, but that's not the word I'm looking for. Example of what it means. So the rule sort of says, okay, I want all the ordered pairs A comma B such that AB is equivalent to, and here we should put 0 comma and like take that number. Cha. In other words, if you really have no idea what integers are, then you don't have to know. All you have to know is that, hey, there's this integer -5. What the hell is -5? Oh, don't worry. That's just shorthand for when you see a little negative in front of a natural number, then some integer is being discussed. What is that integer? It's the set of all ordered pairs such that those ordered pairs are equivalent, via this equivalence relation, to the ordered pair 0 comma, and grab that natural that's like sitting right there. Okay, and therefore, if you don't want to reference once again what it means for this for this ordered pair ordered pair A comma B to be equivalent to 0, 5, then we can just say that -5 is all the ordered pairs A comma B such that B is 5 plus A. I mean, that's kind of even more simple way of putting it. Where A and B are naturals, of course, so this is just done. Okay, and I guess that if we're doing this, this explains what a negative integer is. Well, what's a positive integer? Like, what meaning does the integer 3 get under this interpretation? Because of course, the integer 3 is now going to be a different kind of object than the natural number 3. In fact, I build the integer 3 out of the natural number 3. So what is the integer 3? It's all the ordered pairs A comma B such that, and I see sort of two cases into this definition. Now, if there's no negative in front of the integer, well then it's just all the ordered pairs of naturals which are equivalent to 3 comma 0. Where this 3 is the integer 3, but this 3 is the natural number 3. So these are actually two totally different 3's. This is the the natural number 3, which I'm already assuming exists. This is the integer 3, which I'm constructing out of it. Okay, and I think you sort of see how this works, right? 3 is now the set of all ordered pairs such that 3 plus b equals a. And so it all just works. And the end result is that the integer 3, we're sort of forced to do this, you know, for consistency, is like 5 comma 2, you know, 7 comma 4, etc. And also 3 comma 0, where these numbers are all natural. Okay, so we did it. As long as you give me the natural numbers, as long as I know what the natural numbers are, as long as I know how to add natural numbers, multiply natural numbers, and that all stuff is done, then I can build from the natural numbers the integers. I can prove, we skipped all the proofs, but one can then go on to prove that these objects that we have constructed, these ordered pairs of naturals, behave exactly as the integers are supposed to behave. Then from the integers we can construct the rationals, and we can prove about our rational construction that they behave exactly the way they're supposed to behave. And then, the hardest part of all, of course, which is happening in a separate video, is the construction of the real numbers out of the rational numbers. And then with the real numbers one can construct the complex numbers. And so we really see that lying at the heart of sort of all of modern mathematics is this basic object called the natural numbers. What are they? And that's what Piano was trying to do with his axiomatizations and Dedekind. Okay, goodbye.